So section 3 of your textbook looks at working with equilibrium constants. And one thing to note, because you'll be seeing this frequently, is that if K is large, then the reaction is product favored. That is to say, the equilibrium lies to the right of the arrows. I don't necessarily love the right and left designation, so I like reactant favored, product favored, so I'm going to use that. If K is small, much less than 1, the reaction is reactant favored. Or if you want left and right, the equilibrium lies to the left, and so it lies on the reactant side of the arrow. When we're looking at equilibrium constants, the way the reaction is written matters. So for this first reaction, our K is going to be equal to D raised to lowercase d, E raised to lowercase e, over A raised to lowercase a, B, B. And you would have some value associated with that. In the second reaction, we have E plus D in equilibrium with A plus B. So that's the reverse of this reaction. And when we write K for this, what we'll find is that we have essentially 1 over K. Not essentially, we have 1 over K from this first reaction. So this will be A raised to the A, B to the B, over D to the D, E, lowercase e. And so you can see here, we'll call this 1 and this 2, that K2 is equal to 1 over K1, or K to the minus 1. If we were to take a reaction and multiply it by 2, so let's say we have 1A plus 2B in equilibrium with D plus E, and we multiply this whole equation by 2, we'll have 2A plus 4B in equilibrium with 2D plus 2E. Okay, so for let's call this equation 1 and this 2. For equation 1, we're going to have K equal to concentration of D times the concentration of E divided by the concentration of A times the concentration of B squared. And in K2, we're going to have the concentration of D squared times the concentration of E squared divided by the concentration of A squared times the concentration of B to the 4th, which is equal to K1 squared. So in general, if you multiply an equation by n, in this case it was 2, the new K is equal to the original K raised to the nth power. All right, so what happens then if we add two equations together? So let's look at the reaction. Whoops. Let's change these arrows here. This is incorrect, so it won't let me. Yeah. We're going to have A in equilibrium with B plus C, and then D plus B in equilibrium with A. K1 is going to be equal to concentration of B times the concentration of C over the concentration of A. And K2 is going to be equal to concentration of E divided by the concentration of D times the concentration of B. When we add these equations together, we'll end up with, we've got b, we can cancel out on both sides of the arrow, a plus d in equilibrium with e plus c. And if we write out the equilibrium constant expression for this, I'm going to call this K3, we'll end up with the concentration of E times the concentration of C divided by the concentration of A times the concentration of D. And let's look at what happened with our original K1 and K2. So if we were to multiply K1 times K2, what you're going to see is that we'll end up with K3. And so let's prove that. So K1 was B times C divided by A. Those are all concentrations. Now we're going to multiply that by E divided by D times B. And you'll notice that we'll have B divided by B. Okay, so B divided by B. Those are going to cancel, boom, boom. And so we'll end up with concentration of C times the concentration of E over the concentration of A times the concentration of D. And that is exactly what we predicted here for K3. So when you have two equilibria and you're adding those two equilibria together, the resulting equilibrium constant is equal to the constant 1 times the constant 2. So that's given here.